recording. Chapter 9, gravity, right? Law of universal gravitation. Jenna is right. We really don't know what gravity is. It's one of those things where we don't know why gravity works. Take two objects, hold them close to each other, they attract each other. We don't know why that is the case. We describe that attraction and the force that results. We don't know what a force really is and why it works, but we describe it. We come up with mathematical expressions, and so we believe we have some limited understanding of what gravity is. Next level past that would be to think in terms of electromagnetic waves or gravitons and gravity waves and stuff like that. But we're just moving to the next level, a little less ignorant than we started off with, but that doesn't mean we really know what gravity is, right? But for now, we'll take it on faith, if you will, that gravity works in this way. We don't exactly know why, but we just take it on faith and move on. So gravity is basically, take two massive objects, two objects that have mass, bring them close to each other. What happens is there's a force that draws them towards each other, right? That's what holds us to the earth. The earth pulls us towards it, and that's what keeps us on rather than flinging us off into space. And gravity is what keeps the earth going around the sun. If there were no gravity, the sun would have no hold on the earth, and the earth would just zoom off into space, right? We'd all be slightly dead. I'm sorry? Only kind of dead? Yes, we'd be kind of dead, right? Extra credit to you. Okay, so the force between the two objects, right? The strength of the force is a constant, capital G, called the gravitational constant, multiplied by the first mass, m1, multiplied by m2, the second mass, divided by the distance squared between the two masses. Why is it this precise formula? We don't know. Why is it not some mass 1 to the power of something multiplied by mass 2 to the power of something multiplied by the square root of something else divided by d to the power of 3? We don't really know. D squared we think is related to the dimensionality of our universe.
What's the gravitational constant?
It's a number, and we'll just see that. It's a number that is fixed for our universe. It could be, yes, good job. Point multiplied by something, right? Extra credit. Okay, so it's a number. We don't know why the physical universe, from pure physics viewpoint, we don't know why it has that value. From a philosophical viewpoint, we have a good reason for why these numbers have these values. But from a purely physics viewpoint, we do not know. Okay, moving on to the next slide. So we can actually measure, in principle, the force due to gravity. Here's a massive object, an object with a big mass, m2, and then an object with a mass, m1. Let's say we did not have m2 here. We balance m1 on scales by putting weights on the other side, so the scales are exactly even. Now what happens is we bring m2 beneath m1 and close to it. This then applies a force on m1 and pulls it down. The scales that were exactly balanced are no longer exactly balanced, right? So it tilts towards this mass. Now you add more mass on this side until it evens out, and the amount of mass that you added on that side multiplied by gravity will give you that force of attraction between these two masses. Isn't that pretty neat? That's amazing that we're able to do that.
Would that work with any size object?
In principle, yes. In practice, what happens is the force of attraction is so small that it'll be beneath, like we couldn't do this experiment in our lab here. Okay. We'd have to have extremely sensitive.
Kind of like the moon and the earth.
Yes.
Correctly.
We can measure smaller things than that. Okay. Not with the equipment that's typically available at a college campus, okay. But like in NIST, like in the government labs, we would have scales and so on that are much more precise, right? But so they do a bunch of such combinations of masses, measure these, and that's how you can back out to get this expression. You just plot what is the force as a function of the masses, and you find that it has this relationship. So most of science really is observing what is out there. Science is not able to make predictions about what should be there. Only philosophy is able to make epistemic predictions, right? Science just kind of takes it on faith. We just see this universe. We don't know why we see this universe. We measure it and we describe it. Okay, so introducing the inverse square law. The inverse square law has two components to it: inverse and square. So the intensity of whatever something you're measuring is proportional to 1 over the distance squared. So 1 over distance is where the inverse comes from. The square is here, right? 1 over distance square. So there are lots of things in physics and science that obey this law, like the strength of an electromagnetic field, the strength of light, the strength of sound, the strength of gravity, and so forth, right? So gravity follows this inverse square law. As you go further away from an object, and if the distance doubles, what happens is the gravitational intensity, or the force, drops by a factor of 1 divided by 2 squared. So 1 over 4, it drops by a factor of 4. So this is making the same point. Gravity drops with distance. If you had a really tall ladder, as you climb up the ladder, and the distance from you to the center of the earth increases, the gravitational attraction drops, which means your weight actually decreases. So you can actually plot the force that's pulling you down towards the earth on the y-axis versus distance from the x-axis. Here's 1d. 1d is basically the radius from here to the center of the earth. This distance is 1d. When you go to 2d, what happens is, let's say that your weight is a certain number, right? Whatever. Let's say it's 400 newtons. When you go to 2d, the 400 newton force, weight, has dropped by a factor of 4. So here you are at 100 newtons. When you reach here, it has to drop by 1/9 to 1/9, right? So 400 newtons, which is the beginning, multiplied by 1 over 9, right? So it'll be like 45-ish newtons. Go to 4D, it has dropped to 1/16. 5D is dropped to 1/25. Right? See what's happening? That's why it's decaying. The force is decaying very, very rapidly. And that is an inverse square law. Gravitational force is proportional to 1 over the distance squared. Okay? So, introducing the concept of weightlessness, we on Earth have weight, which basically means that my mass is interacting with the Earth, and the Earth is pulling me down with a certain force. We call that force weight. If we were to switch off the Earth's gravity, what happens to each of you? Yeah, you probably, just the pressure of you sitting, your muscles interacting with the chair and so on, will push you off, and we'll all be like floating around, and there's nothing we can do. Like your center of mass, whatever force you pushed off with, you'll just keep drifting in that direction. You can do everything you want to try to get to a wall, you won't be able to do anything. Because you can stretch and so on, right? In the absence of air. In the presence of air, then you can kind of swim through the air, if you will. Take a while, but... So, weightlessness is a condition encountered in free fall where there is no support force. So you fall out of a plane, don't do this experiment without a parachute, then in principle you are in free fall, right? No.
Superman
Ben-
Six Flags, Superman, when they go
Oh, I see. There's
you hang and then
yeah, okay. So at the very top when you're starting to come down, we'll be close to weightlessness. Okay, cool. Extra credit for sharing that. Okay, so applications of the effect of weightlessness. So a person, don't do this, drives off a cliff. As they fall down, they experience weightlessness. Similarly, if you happen to be an astronaut kind of floating out in space, no particular mass, no planet nearby, in principle, this is not completely true because there will be some net force on you. In principle, you experience weightlessness. Same thing here. If you're on an elevator is stationary and you're standing on bathroom scales, the scales will measure your normal weight. Now what happens if the elevator accelerates upwards? What happens is the scales are applying a force upwards on you, right? Causing you to accelerate upwards. So your weight, what the scales measure, will be your normal weight plus the force that the scales have to apply on you to accelerate you upwards. So your measured weight, your apparent weight, is going to be greater than your normal weight. Now, if the elevator, you've probably experienced this, go to a really tall building, Empire State Building or whatever, and you go through the, like one of those elevators, and you, like the super fast elevators, sometimes in really tall hotels. As the elevator drops, what happens to your tummy? Sorry?
you feel sick.
Yeah, you feel kind of sick, right? Like almost like, ooh, it's like I'm feeling weightless. That's because of this. What's happening is, as the elevator accelerates downwards, your weight all of a sudden becomes lighter, right? That's part of it, and then part of it is also that the inside, your insides try to end up like higher than they normally are.
Kind of like with water, when you're carrying someone in water, is they're lighter.
Okay.
And when
Oh.
Is that?
Um,
I don't know.
That is buoyancy. We'll see that in a future lecture, right? But extra credit for bringing it up, right? Okay. So if, don't do this experiment, but if the chains, the cords, whatever holding the elevator up, all the chewing gum, all the kind of stuff, if that falls apart and the elevator drops freely, what will happen is you will experience zero weight. So you'll have the fun of a weightless experience for a while. Yes, sir.
I'm just kind of curious. It's not really clicking with me. I get that because I've experienced it, but weight's like the force of gravity on you, right?
Yes. By definition, weight is equal to the force that gravity applies on you. Therefore, here we should not say weight. We need to call it apparent weight. So we're going to feel lighter, but you're right that the force due to gravity is exactly the same on you.
So if you're going up, it's just pushing harder on you?
Yeah, if it's not just if the elevator is moving up, but if the elevator is accelerating up. If it's moving up at a constant velocity, your weight will be the same as your normal weight, and the measured weight. So when we're talking about weight here, we're really talking about what number you see on the bathroom scales. So you're standing on the scales, right? Let's say it says 150 pounds, right? And what happens is when you accelerate, the elevator is accelerating up, you will actually see the dial go up. So it'll go to whatever, 155 instead of 150, some number.
Opposite of gravity?
What's happening is, because the bathroom, that's an artifact of the way the bathroom scales are measuring your weight. If you stand on bathroom scales, the bathroom scales are not measuring the force that you're applying on the bathroom scales. The bathroom scales are measuring the spring reaction associated with the force that the bathroom scales are applying on you to counteract your weight. So the bathroom scales are really measuring the upward force that the scales are applying on you, right? In a stationary environment, that's the same as your weight. But if your elevator is accelerating upwards, what happens is the scales are having to apply a greater force on you than your weight to get you to accelerate upwards. So it's going to measure a greater number. And if the elevator is drop, it's accelerating downwards, the scales have to apply a lower pressure on you, force on you, because it doesn't have to completely counteract the acceleration due to gravity.
Okay.
And so you will read an apparent number that's lower. Right? So even though we're calling this weight, really this is the number that the scales are measuring. So it's the apparent weight or the measured weight. It's not the real weight. Good question, extra credit. Okay, introducing tides. You all know what the tide is, right? If you go to the Phoenix Ocean and you look out, right, as the moon is lined up, what happens is the water. Okay, for those of you who have never seen a tide, I may have to show you a picture. Okay, let's go to the next slide and come back. You all know this, right? If you go and look out at the Phoenix Harbor, and if you look at the water level there, okay, either two students are awake, or you guess it's obvious that everybody else has seen the Phoenix Harbor.
The fake Phoenix Harbor.
There is one.
Have tides.
Oh, it does. Yes. So if you go to the Phoenix Harbor or to the Phoenix Ocean, and if you have a boat that's kind of tied up to this, whatever this is, jetty or whatever, you can see at low tide the boat is lower, the water level is lower. At high tide, the water level is higher, right?
Yeah.
Oh, the same fish that we saw in the previous slide, right? Yes. Okay, so what is happening with spring tide versus neap tide, which were the definitions on the previous slide? The tides happen because the moon is pulling on the water. The gravitational attraction of the moon is actually pulling the. Isn't it amazing? Yeah. So let's say here's the moon, and here's the Earth, and what happens is here's the oceans around the Earth. The moon is actually pulling the oceans forward. So it's like the Earth gets a beer belly, right? And the beer belly is always facing the moon, presumably because it thinks that the moon is the source of the beer or whatever, right? So here's the beer belly. Turns out there's also a beer bottom or whatever, right? And that makes sense. I'd never ever heard of a beer bottom, but it makes sense that there should be one, right? If there's a beer belly, right? Okay, so not that I've ever made an investigation of such a topic or ever have an interest in okay, with that caveat, we'll move on. Okay, so here's the beer belly. It's because of the moon that's pulling the water towards it compared to the Earth, right? So in the case of now the sun is doing the same thing. The sun's gravitational attraction is pulling the Earth's water towards it as well. if the two of these are lined up, so here's the sun, here's the moon, and they're both pulling the water in the same direction, you'll end up with a higher high tide. Right? So that is a spring tide. So in the spring high tide, what happens is the high tide is like way higher than the normal high tide. Now a neap tide is where the moon is acting against the sun. So in this case, it's not that the moon that's on the other side, the moon is at right angles with respect to the earth, right? So draw a line from the sun to the center of the earth, draw a perpendicular, the moon is like along the perpendicular-ish, right? So in this case, what happens is the moon created beer belly is trying to point towards the moon. The sun created beer belly is trying to point towards the sun. So what happens is the moon is trying to create a bump of water here, the sun is trying to create a bump of water here. So they're working against each other, which means then that the high tides will be not as high and the low tides will be not as low. So in an example like this, these regions are experiencing a low tide in this picture, right? That's a low tide and that's a high tide. Low tide, high tide, low tide. So that's what the spring versus neap tide is about. Okay, introducing the concept of a gravitational field. A field is basically a sphere of influence. Here's an example of it. Students sometimes have difficulty thinking of what a field is, because we're going to talk, actually, yes we will, about electric fields, magnetic fields, gravitational fields and so on. So you probably all experienced a perfume field. You all know what a perfume field is? Right? Okay, person walks in the door, they're wearing one of those completely choking, like cloying perfumes, right? The kind that kills you. So what happens is they walk in the room, and let's say they're standing here, and what happens is a second or two later, you guys are all like wondering what's happening. The front row of people are like starting to hack and cough, right? And you guys are all, what's up with that, right? Why are they all having difficulty breathing? And what happens is 2 seconds later, now you guys are starting to hack and cough, and these guys are starting to kind of get woozy, right? Now another second later, what happens is the last row is starting to hack and cough, you guys are getting woozy, and these guys have passed out, right? So this is an example of a perfume field, right? Sphere of influence of the perfume. The person comes in, and the perfume, as it spreads, it has a very strong impact on the people that are close to this person, and a lesser impact on you, and even lesser impact on you, right? So the same thing. Let's say that we were to bring the earth here, right? We bring the earth here, or we bring the sun here, whatever. The moment we bring the sun here, a gravitational field starts permeating this area. What happens is you guys sense it first. You guys don't yet. You sense it first, and you start getting attracted towards the sun, or the earth in this case. And then a little while later, you guys, right? And the force of attraction is the greatest on you guys who are closer to the sun or the earth compared to the rest of you. So that is an illustration of the gravitational field, right? Kind of like a magnet, yes. Yep, extra credit. Magnet does exactly the same thing. We talk about a magnetic field. It's a magnetic sphere of influence, right?
Why does that only apply to massive?
Why does it what?
It just specifies massive bodies. Why does it only apply to larger bodies?
Oh, actually it applies to any body.
Okay.
Any body that has a mass,
Okay.
right? So even a small particle that has a mass, as long as it has a mass, will be influenced by this. The greater the mass of the objects, the greater the force, right? Extra credit to you for the question. Good. I'm glad to see you speaking up and asking the questions. Okay, so illustration of gravitational field. So here's the earth, and what happens is the gravitational field, you can draw the gravitational field as a series of arrows, where if I were to take a 1 kilogram ball and place it here, what is the force on that kilogram ball? 1 kilogram mass, I place it here.
The mass of the ball to the mass of the earth over the distance
Squared.
times the gravitational.
Times the gravitational constant, g. That's amazing. Extra credit to you. Wow. Okay. So you're right. And the direction of the force is towards the center of the earth. That's why this arrow is pointing in that direction. If I place it here, it's towards there, here, there, right? So you draw this, place the sphere at different places, draw those arrows, and you get your field. Wait, Monsieur?
Did we place a number on the gravitational constant, or is it just different in every instance?
This gravitational constant g is actually given in your textbook. It's like 6.7. You said 6.67 multiplied by some number. I forget what.
I think it was.
Sounds reasonable, right? So multiplied by mass 1, mass 2 divided by the distance squared. Now this g appears to be fixed for our entire physical universe. We don't know why that is the case. It's actually, to a first approximation, it's an assumption. It's an assumption. It's an assumption of faith that the gravitational constant capital G is the same throughout the physical universe. In principle, it is possible for capital G to be different in different parts of the universe. The odds are that you will get a Nobel Prize if you can demonstrate that to be the case, right? So it's something you can do this weekend if you wish, right? And if I haven't made this offer before, if any of you get a Nobel Prize before the semester is over, you automatically get an A. You don't have to do any more homework, right? Sorry?
So you just have to work on getting a Nobel, huh?
Yeah, you can get the Nobel this weekend or something like that, then you're totally set.
I don't think they award them that quickly.
I'm sorry?
I don't think they award them that quickly.
You may have to influence them. You what? You can. Okay, if they don't award it, then at least get nominated for it. Sorry? Okay, so application. So the force due to gravity is the gravitational constant multiplied by mass 1 multiplied by mass 2 divided by the distance square. So let's say that we have the Earth. Okay, that's a star with a certain weight. Size, right? So here's the radius of the star. The person on the surface of the star weighs 10,000 newtons. Take the same star and shrink it. As the star shrinks, so you have shrunk the star so that its radius is now half what it was to begin with. The weight of the person goes up by a factor of 4. Right? 10,000 becomes 40,000. The reason why it went up by a factor of 4 is because the distance dropped by half. So it's going to be half square. So half square is 1 divided by 2 square, which is 1 square at the bottom multiplied by 2 square on top. 2 square is 4, right? And so if you're puzzled about that, just take half, which is 0.5, square it, it'll give you 0.25, then invert it. 1 divided by 0.25 should give you 4. So this will become 4 times. What this tells us, if you take the Earth, right, let's say that let's say that your weight, colloquially speaking, is, pick any number, 140 pounds. If your weight is 140 pounds, okay, the math, that's harder. So I'm just going to go with 150, right? So your weight is 150 pounds. If we were to take the Earth and reduce its diameter by half, and we're still on the surface of the Earth, your weight will go up by a factor of 4. So you would weigh 600 pounds. And our frames are not built for it, which would mean that we'd probably all kick our respective buckets. Just die sooner, like a heart to have difficulty pumping blood up and down, right? And so forth.
So I have a question.
Mm-hmm.
Is that the figure then that they get our gravitate, 9.8?
Okay, we'll come to that in a future slide, I believe. What happens is the 9.8 comes from the fact that weight is equal to mass multiplied by gravity, by little g, and we'll see that. Remind me if we don't see it later in this slides, right? That's a good segue, by the way. Oh, it didn't show up. Then it'll be in a future lecture. Okay. So, yeah, okay. So, you know that weight W equals mass M multiplied by little g, right? We've seen that already. So, if you look at this expression, let's say that this is my mass, M, little, right? M1. Everything else in this can be consumed into one entity and call that little g. So the force due to gravity, which will be W, is equal to my mass multiplied by little g. So little g has the rest of this, which means the acceleration due to gravity, the little g that we've already talked about, is equal to the capital G multiplied by mass of the Earth divided by the distance between me and the center of the Earth. Right? So this is just for your understanding. You don't need to know this at this time, right? But just be aware. Okay, introducing two other concepts: a black hole and the Big Bang. A black hole is a hole that's really black, and a bang that's really big is a Big Bang, right? So we're cool? We're not? A little more explanation? Good? Okay. Okay, a black hole is where you take a mass and you concentrate it, like you shrink it so much. Take a star, just have a bunch of people pushing all from all the different directions, get the star to get smaller and smaller and smaller. At some stage, the gravity at the surface of the star becomes so big, even light is not able to escape. So if light is no longer be able to escape, so any light that comes and falls on the object does not escape. It does not get reflected or re-emitted. So the object becomes totally black. right? So if you look at, what's your name? Jeremy. If you look at Jeremy's t-shirt, notice that he's wearing a black t-shirt, right? And if we look at Mike, right? Okay, if you look at Mike's polo shirt, it's green. What is happening is white light is falling on Mike's polo shirt, and the polo shirt is absorbing all the colors except for green, and green is being re-emitted, or reflected if you wish, which is not completely right. And that's why his shirt looks green. If you look at Jeremy's shirt, what happens is white light falls on it, and all of the light is absorbed. So, because it's absorbed, his shirt looks black. Now, we can see some features on his shirt. The reason why we're able to see some features is because of the fact, even though it's all black, there's a certain amount of reflectivity or emissivity of the portions. That's why we're able to see that, right? So, a black hole would be like taking an orange, what's your name? Rebecca, right. Is that orange? Okay, like taking an orange top and changing its behavior, right? So that it now absorbs all of the light instead of re-emitting the orange. And so what happens is when we look at your t-shirt, it looks exactly the same as Jeremy's. So take a star, compress it, typically due to gravity, so much that its gravitational attraction becomes so strong that light is not able to escape. So anything that falls on it is totally absorbed, and that's what we call a black hole.
So it's not actually a hole.
It's not a hole. It's just like physicists will sometimes come up with terms that don't make so much sense. It would look as if it's a hole, but okay. The Big Bang is, if you look at our physical universe, it's expanding over a period of time, right? So what happens is, if you look out at space, you can see the stars running away from us. The indications that the physical universe is expanding. So if you look at the size of the universe right now, let's say it's this big. 100 years ago, it was a little smaller. 1 billion years ago, it's smaller. So you can extrapolate backwards, and we get to about 13.7 billion years, say 14 billion years ago. What happens is, all of the matter and energy in the physical universe was compressed to a tiny little point, and prior to the point did not exist at all. There was no matter, no energy, no space, no time prior to the Big Bang, prior to the 13.7, 14 billion years ago. So the Big Bang is this takes us into philosophy, right? So if you happen to believe that there is no God, the Big Bang really, it's just an event that happened. We have no idea how and why. If you happen to believe that there is a God, this can be viewed as a creation event, right? That a non-physical entity who then created physical material, that is matter energy at this instant, which then expanded outwards to create all the matter, all the energy, the space and the time that we observe in the physical universe. Was it a question?
Well, I'm just wondering if there are people who believe like something in between, like maybe the small like pinpoints of energy actually always existed, and then, or because of the theory, does it just kind of go to nothing?
It's interesting that the physics indicates that nothing existed prior to the Big Bang. Like I think it's the Hawking's-Hartle theorem basically indicates that there was no matter, no energy, no space, no time prior to the Big Bang event, right? So that seems to be, there are people who speculate that something existed prior to that, but there's no physics or science to substantiate it, right? Okay, so Einstein's theory of gravitation, basically he